For today's presentation, I'm gonna introduce my lab's research related to the 4D bioprinting for tissue regeneration. Or maybe the topic a little bit different from other speakers, but I think I really learned a lot from all of the excellent talk. I want to introduce some different things here. If you use only one word to describe my lab's research, I'm going to use regeneration. I'm not sure. Can I go next slides? Okay, here you can see that. So my lab right now uses the tissue engineering technologies. Majorly, you can see the picture highlight here, the several key components in tissue engineering. One is the cells. For example, you maybe heard like stem cells, different stem cells for tissue regeneration. But only the cells is really hard. You can get pretty larger tissue organ constructs. There is another very important key component in tissue engineering research is scaffold. So that's the part bioprinting, like 3D, 4D bioprinting can contribute a lot to print biomimetic scaffold, either with the cell together or separate to support the cell growth and the tissue regeneration. So in addition, I think other different technique like mechanical stimulation, electrical stimulation, and also adding different growth factors into the printed or fabricated scaffold with cells are also widely studied. But the final goal is to create artificial tissue or even organ to replace the damaged part in human body. Okay? So right now in my lab, we consider we have two key pillars. The first one related to the bioprinting, like printing the cells, bioactive factor, and also biomaterials into either like a patient-specific, very complex tissue organ constructs. So in addition, we also design different bioprinter for different application, like we build the sterilization-based printing system, use the UV laser to photo crosslink, we call it resin material. The other is the fused deposition modeling, use heat, melting the polymer. We also build the bioplating-based printing system and also inkjet bioprinting. So recently, we also have another digital light processing-based printing. So that's for different tissue regeneration applications. For example, the slides here just highlight several printed tissue constructs using different printing mechanisms. Like the picture highlight here is the sterilization. And also based on the design part, we can also print different geometry, different thickness. Some used for like a vascular network fabrication, like a blood vessel system fabrication. Some for the neural and also musculoskeletal tissue regeneration. Okay. The second key pillar related to the nanotechnology, which specifically refer to the nanomaterials, very tiny materials with basic structural units smaller than 100 nanometer in at least one dimension. There are two major reasons we want to use nanomaterial for the printing application. One reason is we want to create a biomimetic scaffold. We want to mimic the natural the human tissue structure. They have a lot of nanometer over there. For example, they have the nano-structured extracellular matrix that's surrounding different cells. There are also many papers already reported the nano, like the matrix can improve the cell behavior. So that's the reason we want to create that nano feature in our scaffold. But the other is related to the limitation of current many 3D bioprinting system. They can print pretty cool, like micron-sized scaffold, but it's really hard to go to the nanometer in dimension. So there are some nano printer available, but normally fabricate pretty tiny objects. So for larger tissue organ, we need a pretty larger printing is really hard to achieve. So that's the reason we're thinking we maybe synthesize some nano material as the ink, like using the nanoparticle, nanotube, like self-assembly DNA-based nanotube, and also fabricate some cold shell nanosphere can loading the drugs into the center part. And the nanocrystalline hydroxyapatite normally for the bone, like hard tissue regeneration because it's the bone minerals. In addition, we also work on the graphene, like a carbon-based nanomaterial mixed with gel and then printing them for different applications. In the following, I'm gonna focus on the 4D printing, especially related to the smart material and also integrate with the nanomaterial for different applications. Okay. For the 4D printing, I think you all expert in this field. I also heard so many exciting talk related to the 4D printing. In my lab, we use several ways to realize the 4D bioprinting. One way is we use some shape memory-based natural smart material for 4D bioprinting. We synthesized the material from the plant oil. It's called soybean oil-based material, and also use the stereolithography-based the laser printing system to fabricate the constructs. I'm not sure you can see the image here. Majorly for the bioprinting application, one of the very key criteria we need to consider is the biocompatibility, which means they are safe to cells, no toxic. That's very important. So that's the reason we first evaluate our soybean oil-based material biocompatibility using stem cells from the human bone marrow. We also compare to other bioprinting material widely used like PEG-DA, PCR, or PRA. So I think the PEG-DA, the cell proliferation is a bit not ideal, but PCR, PRA already approved by FDA for many medical device, drug delivery, different things, applications. So our soybean oil-based material, the biocompatibility pretty similar to that two materials, so can proliferate pretty well on our scaffolds. So in addition, based on different design like in-field density, we can also print the structure pretty easily by the stereolithography-based printing system. And also the material themselves is temperature-based shape memory material, which means we can change their shape based on the temperature change. We can fix another temporary shape at a lower temperature, but if that structure go to the body temperature, they're going to recover to their original shape very quickly. So the second way, we also do some pretty simple anisotropic smart structure design, like a cross structure with 2 layers only. Each layer, they have different patterns. And also after that, the laser printing, different pattern, they can create the surface tension imbalance between top and the bottom layer, and they can self-rolling differently, especially the last column here, they can rolling the most when compared to other design. So that's another way we create a smart structure. In addition, I'm not sure the video can be played. Okay. In addition, we also found this printed structure can change their shape based on different solvent system. For example, if we put the printed structure into an ethanol solution, you can see the video here. It can like a flower blooming. And then we put the open structure into a water solution, and they can close. It's a reversible process. I think that's not our intended design. Just during the experiment, we discovered that very interesting phenomena based on the solvent changing the shape. Okay, and also the fundamental material, as I mentioned, is shape memory material, which means they can change their shape based on the temperature changes. So you can see the video. So we can fix another shape, temporary shape at a lower temperature. But if you put them into a body temperature, they can quickly recover back to their original shape. Okay. So that's the smart material only based on the polymer. But we're also thinking maybe adding some nanoparticles. For example, here is the graphene into the printing ink. So they also achieve another very interesting phenomena under the light. You can see we adding different concentration graphene into the smart material from lower to a little bit higher. But we normally don't add too much because we consider as the bioprinting application. So if you add in too much, maybe not very safe to the cells. But we found out after adding the graphene nanoparticle into the constructs, they can change the energy absorption when we do the laser printing process. And then under the UV light, they can change their shape differently. You can see higher concentration, they can change their shape further when compared to the control and the lower concentration graphene over there. And we also fabricate different, like the pattern, like GW pattern, a cubic, sunflower. So under the light, they can also self-folding, change their shape automatically. Okay. So there is a video here highlights the light-based graphene incorporated 4D shape changing. So the polymer themselves are transparent. By adding the graphene over, they become black color. So by shedding the light, they can like open. We also print a different structure. So under the light, they can change their shape. And also because graphene is also conductive, so you can see the structure unfold, the light bulb is also on. So that's pretty good for some conductive biomedical application. For example, like a neural tissue regeneration, you can apply the electrical stimulation into the constructs as well. So the last two, just some model demonstration, so they can pump up red lights. Okay. Okay, so that's the several mechanisms we use to do the 4D shape changing. More importantly, we want to use that for the application. So that's very important. I heard from Martin's excellent presentation about the potential application related to the cardiac tissue patch. So I'm going to mention some briefly information in my talk also. I think one application people thinking using for the biomedical application is related to the minimally invasive surgery. So like you can print a bigger structure and press them into a tiny structure. Either can be injected or very easy to implant it into human body. And then they can pop up inside the human body. Another is, I think, the pediatric device design is very important. I think the Martin mentioned. So because the kids, they're gonna grow up, but the pediatric device right now, they just a smaller size compared to the adult device. They don't have some unique smart feature can grow up. Yeah, so that's another application can expand for the long term. So for my lab's study, because sometimes it's not very easy to realize the expanding one. Initial point, we're thinking one application can be used for stem cell, like a functional control. For example, here, that's the first application we used is print a smart self-morphing culture substrate, which can be used to control like neural stem cells differentiation, because the neural stem cells is a very unique cells. They initially, they prefer to aggregate to a neural sphere, but later they want some aligned pattern to guiding the neurite extension and the connection. So that's need a dynamic shape changing process. So we're thinking, because traditionally the neural stem cells, they just use a static culture system, the Petri dish, without any change, even for the 3D printing, just the static, either different porosity or there. But we are thinking maybe use the 4D printing, we can fabricate the constructs, initially have some microcircular pattern, but that microcircular pattern can be slowly disappeared in 1 week. So you can see here. And then replaced by the highly aligned pattern. So initially we contribute the neural stem cell aggregate together, but later we guiding the neurite extension with the aligned pattern. We also seeding different like cell density into the constructs. We also evaluate their proliferation and find out the microcircular pattern can contribute the cell like aggregate into the chamber part. And in addition, you can see more clearly about the shape changing process using the picture here. That's the light microscope image. You can see initially they have the circular pattern. The cells go to that spot. And then over the time, after 1 week, that spot gonna disappear fully with only highly aligned pattern over there. So we also do pretty thorough study about the neural stem cells function, like gene expression analysis, the imaging, different technique. I won't show all of the data here, but just the one I want to highlight, like the neurite lens, we normally evaluate like which constructs can promote the most neurite extension, which means it's better than others. So the control is a flight construct without any topography change, just a flight. The middle one is also a static culture system, but they have the highly aligned pattern already fabricated on the surface. So the last one is called dynamic shape changing smart constructs. So initially they have the macular circular pattern and then disappeared and with the aligned pattern. So we found out our dynamic culture system can facilitate the cell early proliferation and the later differentiation, got much better results like neural differentiation when compared to the static controls. So that's very promising because there are many potential applications. For example, right now there are many study like assemble different cells into a sphere organelle. So maybe using that construct can also help to contribute to that. So that's the one application, control the stem cell differentiation. The second one, we are starting to work on like the cardiac tissue patch fabrication for heart repair. So you maybe heard the heart attack is very severe disease in human body. So the major reason is because in the blood vessel in the heart part is blocked. And then that area, the muscle without any blood supply, without nutrients transportation, the tissue gonna die and the heart can stop beating. Right now for the research side, there are no many progress. There are many studies they using like a stem cells injection, like directly inject to the patient's defect part. Hopefully the stem cells can healing the damaged tissue. But you know, the heart is a beating organ. It's really hard. You can keep the stem cells into that location for longer term. So that's the reason right now in the field, there is a very promising, also popular research direction is called the cardiac tissue patch fabrication. So it's you can see the picture here, just can be a very thin the tissue, maybe hydrogel based. So they can help to deliver the cells into the defect part much easier and keep there for longer term. They can also provide mechanical supporting and the biophysical integration. In order to design some biomimetic cardiac tissue patch, we also look into the native like myocardial tissue, their structure. They have the inostropic hexagonal kind of like that structure. So that's the reason for our cardiac patch design. We just use the very simple design. One is control with a square pore, we consider as the isotropic patch, and another with a hexagonal pore inostropic patch. We also evaluate a material like a different ratio combination, make sure their modulus pretty similar to the native human heart myocardial tissue. So we combine the PEG-DA, the gelatin methyl acrylate at a different ratio, and find out the gelatin methyl acrylate, I think is 5%. The PEG-DA 15% is pretty good, similar modulus. And more importantly, we also use the IPS, called human-induced pluripotent stem cells. You maybe heard that one because it's really popular. Just several years ago, the inventor, I think a scientist from Japan, won the Nobel Prize because discovered that artificial iPS cells. So we use that cells differentiate into cardiomyocytes sitting on our construct. It's also pretty well compatible. Okay, and also we found out by changing the printing speed, we can also let the scaffold self-rolling slightly can fit to the human heart or animal heart, the curvature part. So the 4D here is very simple, just the curvature fitting over there. But then we really want to design some more smart design, either expanding or maybe beating with the heart, but there still have a lot of challenge. So hopefully in the future, we can discover some new things. More importantly, we also evaluate because we need to deliver the cells into the heart. So we also need adding the cells over there. So we use 3 cell lines because normally in human body, tissue organ, they have many cell type over there. Normally you cannot use only 1 cell line. Only the cartilage is only 1 cell line. For the heart, you need to have the cardiomyocytes. That's the major, the cardiac the cells contribute the beating part. You need to have the endothelial cells because that's the blood vessel cells can contribute the blood vessel formation, provide the nutrients transportation. We also need the human mesenchymal stem cells to mimic the human cardiac fibroblast. So that 3 cell line, we also evaluate what's the best ratio. They can survive in our constructs and also further proliferate, differentiate better. So we found out the ratio here, 1:2:2:4 is pretty good. For the tissue engineering research, another very important one, especially for larger tissue organ regeneration, is bioreactor system. I'm not sure you heard. Bioreactor is kind of chamber. You can control the environment, oxygen, carbon dioxide. You can control the flow rate. Is mimic the human body environment. You can also apply a lot of stimulation into the system. We also consider that as a dynamic culture system. So we also found out in a bioreactor we designed in our lab, so the cells can differentiate much better when compared to a static culture, just to put them into a dish. Okay. So in addition, besides in the lab, the cell culture study, we also do the animal study. For the in vivo heart implantation, we use the mice. We have the 3 animal models here, maybe a little bit bloody, so but I think normally for surgery it's just a small case. So they have even more bloody like the surgery. So one is the normal mice without any injury, just attached our patch into the heart to see whether they can keep there for long term. Is there any detachment over there? So the second one is a very simple injury. It's called electric burning injury. We create some wound area on the surface of the heart. We want to evaluate the integration of the patch with the mice heart, whether there are some cell migration, vascularization like that. The last one is the model we really want to evaluate. It's called the myocardial infarction model. So that's mimic the real disease. And then we attach the patch over there. I think for the normal model, so our patch can attach there, the heart beating all normally without any side effect. And also the data I only show one here is the last model. We do that study for 4 months. And also we observed many promising results. One is the patch can, like a self-curvature, they have the self-curvature, can fit to the mice heart perfectly without using any glue. So sometimes when surgeon do some surgery, they maybe use some glue to attach the material into specific location. But our material can just attach there pretty strongly for multiple months. And also using the imaging, like MRI, and also histology, cutting the tissue. We also observed a pretty good vascularization, and also the iPS cardiomyocytes survival is also pretty good. They also see some integration, cell migration into the native heart tissue, because that's very important. So we expect the cells not only in the patch, they need to migrate into the damaged part, like repair the tissue over there. So the integration is always very important. So I think based on that promising results, right now we plan to do some pig study in the future, because mice, we just evaluate some very basic function of our 4D printed patch, but the mice heart is very tiny and beating too fast. So pig has the similar size to human heart, so we can get more meaningful results from the pig. Okay, I think I probably gonna stop here. So I would like to give the credit to my brilliant postdoc, the previous postdoc performed all of the study, and also my PhD students team and Zhang, Dr. Haitao, Dr. Stamiao contribute a lot on the 4D bioprinting material synthesis, and also for the animal study, all of the in vitro work. And also my collaborator, especially for the animal study, we collaborate with the NIH. They contribute to do the animal surgery over there. Okay, and also the funding support. So thank you very much for your attention. I would like to answer any question you have.